All right. So it's a great pleasure to introduce Evgeny Shinder from the city of Sheffield, city which has a long history, not only as an industrial center of Great Britain, but a city where one of the greatest movies ever made, The Full Monty, was actually shot. So it's a pleasure again. Zhenya?
Okay, thanks, Ludmil, for the introduction and the invitation to this conference. I'm happy to give a talk here. It will be about factorization centers and the Grothendieck ring. So in terms of the topics of this conference, it will be more about rationality and less about Hodge structures, but still things like intermediate Jacobian as an abstraction to rationality is one of the themes that has inspired this work as well as other more modern developments. So let's begin. There'll be some motivation and at the same time, the main question I'll be talking about. So the question is quite simple. We take a smooth projective variety and a birational automorphism, and we ask whether centers that phi blow-ups are in bijection with exceptional divisors that phi contracts. It's natural to request a bijection which preserves some geometric properties of those centers and exceptional divisors. For example, we can ask whether we can match up the centers which will blow up with exceptional divisors which it blows down, preserving stable birational types. So I'll give two examples now. One will be example and the other will be non-example. So firstly, here is where Hodge structures come in, is in three folds. This question is completely controlled by intermediate Jacobians. Namely, let's take a rationally connected smooth threefold and a birational automorphism of it. And imagine that phi blows up certain curves of positive genus. I ignore curves of genus 0 for the time being. They are easy to reconstruct. And then it contracts certain ruled surfaces over other curves of positive genus. Then by the intermediate Jacobian argument, namely, every time we blow up a curve, we get a copy of the Jacobian of that curve inside the intermediate Jacobian as a principally polarized abelian variety. And conversely, when we blow down a ruled surface to a curve, we remove a summand. And by the uniqueness of decomposition, these curves which we contract will be in bijection with those that we blow up. Right, so this is one thing. In dimension 3, it's completely understood.
Zhenya, but the bijection need not to be canonical, right?
Yes, that's right.
If you have several isomorphic curves, it's unclear how to find
that's
the
right.
bijection.
So if we blow up isomorphic curves several times, this procedure doesn't give us a canonical identification. Yeah, that's right. And the second example is non-example. So we look at complex fourfolds and at a certain map constructed by Hassett and Lai. The map by construction blows up a K3 surface in P4 and contracts a ruled divisor to another K3 surface in P4. And then the beauty of this construction is that S and S prime are not birational. So something which couldn't have happened for curves happens here in that one dimension up, that those surfaces are not birational, and also because they're K3s, they cannot be stably birational. Those surfaces will be L equivalent, which is a concept that I'll be speaking about a bit later. So we see that sometimes the answer is positive to my question, sometimes it's negative. So let me turn to the main subject of this talk. This will be surfaces, but to make it interesting, we'll look at non-closed fields. So there's a bit of arithmetic flavor to the whole story, but there will be lots of geometry as well. And before I give the main result, let's just give an example of a map I may be caring about. So I look at standard Cremona transformation of P2, which blow up 3 points and contracts the lines connecting those pairs of points. And over non-closed fields, it's a bit better to think of Galois actions of those on those points. And I prefer to blow up a Galois orbit of 3 points and contract the Galois orbit of 3 lines connecting those pairs. And it's clear that these orbits are isomorphic. So that's an example for the main result. So we have a smooth projective surface over K and look at any birational automorphism of this surface. And then we choose any decomposition of phi into blow ups and blow downs with smooth connected zero-dimensional centers. So let's say phi blows up those schemes, so Fi's are some fields, and phi contracts P1 bundles over some other schemes, where again Fi are primes are fields. So the result is that the number is the same and the fields are isomorphic up to reordering. Again, like in the Clemens-Griffith story, this is a non-canonical identification. So kind of the proof of this, so the theorem looks a little bit formal, but the proof involves checking all birational maps between all minimal models. So there will be lots of geometry going into this theorem. Are there any questions or comments now? Okay, so we move on. I'll explain the plan and then we go through these topics. So first I'll define the invariant which will take care of the centers I blow up and blow down, and I state the main results in a couple of different ways. Second, I explain the consequences of the main result for the Grothendieck ring and connection of what I do to the Grothendieck ring. And finally, I give some proofs, mostly in the rational surfaces case, which will involve a minimal model program and Sarkisov links. So in this talk, we deal mostly with surfaces over non-closed fields, and there's a slightly different story, higher dimensional story over C and other fields. And I talked about this in the Simon's conference on rationality. The talk is recorded. Please take a look if you're interested. Okay, so I'll start with the definition of the invariant, which takes care of the centers. Firstly, we need to discuss where does the invariant take place. And the centers of the blow-ups for surfaces are, as I said, zero-dimensional schemes. So we'll be thinking of them as Galois sets. So we blow up and blow down centers. What are the centers? In this setting, the centers are connected smooth zero-dimensional schemes. So I can think of them as points with Galois action. Galois descent is a device which identifies those zero-dimensional schemes with sets with GK action. So this is partly why I feel this to be perfect, because there will be lots of Galois theory in place. So the placeholder for my invariant will be the Burnside ring of the Galois group. So let me remind what the Burnside ring is. Generators are isomorphism classes of continuous finite GK sets. And relations are sort of cut and paste. So disjoint unions are becoming direct sums.
Zhenya, what does continuous mean?
So Galois group is profinite, and you have a finite set with a discrete topology, and you want the action to be continuous for these two topologies.
Isn't it automatic because it is finite?
There's an example of subgroup of finite index in the Galois group, which is not open. So basically you want open stabilizers.
Okay, sorry.
It's a little bit subtle, but continuous is not automatic. Okay, so there's no cancellation problem in this ring. Okay, I'm using the group structure here. So this is a free module with bases given by transitive sets. That's obvious from the definition. Everything splits into orbits, and the orbits are independent. So an example for this object, if we look at the field of real numbers, we have Galois group Z mod 2Z, and there are two transitive sets Z mod 2Z can act on. Either it's a fixed point or it's two elements permuted. And this is the basis for my Burnside ring. So this was the first slide about this story. I'm looking at this object which contains all finite Galois sets. Now I want to make an example, and this example will be relevant in what I'll be speaking about later on. So let's take everyone's favorite, a cubic surface over a field, and we have the following Galois sets. So this goes back to, yeah, so I give some sets attached to the surface and state their order. So for example, the set of lines on a cubic surface is a Galois set of order 27. Now we can look at pencils of conics on X. Again, this is a Galois set. And in fact, the standard argument is that those pencils of conics are in natural bijection with lines, namely look at residual lines to a conic or residual conics to lines. And therefore, it's also 27. And now I wonder if we have experts on Del Pezzos in the audience and whether anyone would tell me how many nets of twisted cubics there are on X.
72.
Oh, thank you, Sasha. Yeah, excellent. So we do have experts in the audience. Yes, so that's a fun exercise to compute by presenting all those twisted cubics in the blow-up model of a cubic surface, and you get this many linear systems. Okay, and later on we'll care about Galois sets like this when we study rationality of Del Pezzo surfaces, for example. Okay, so just some more words about this Burnside ring. So other...
What about Eckhart points?
Eckhart, it depends. So up to 18, right?
I don't remember.
In characteristic 2, up to 45. Right, so other ways to define this Burnside ring is, so if you think about birational geometry, these are zero-dimensional birational types. So birational types of zero-dimensional schemes are the same as their isomorphism types, and it's the same generators. So in the modern language of Kontsevich-Schinkel Burnside ring, this is the 0 bit of the big Burnside ring, which includes all birational types of all dimensions. And another language which is often useful is to think of those Galois sets as field extensions or étale algebras. So you have a finite field extension, then the corresponding Galois set is the set of maps from embeddings from this field to K bar, and standard Galois theory says that it's a bijection. Okay, so I've defined where the invariant will take values. Now let me define the invariant itself. So the way I present it here is via axiomatic properties. So I'm constructing a map which is called C from birational morphisms between any pair of surfaces to this Burnside ring I was talking about. And there are 3 properties it satisfies. Firstly, any isomorphism goes to 0 under this map. Secondly, we need to specify what it does on each blow-up. And there's some choice of sign involved, but I want C of phi to be minus the center of the blow-up and C of phi inverse be the plus center of the blow-up. So this way, if I have an arrow from x tilde to x, and if x is sort of bigger than x tilde, then C of phi will be positive. Okay, it doesn't matter very much which convention I chose this one. So it's maybe this phi inverse is explained by the next property is that for composable birational isomorphisms, I want the sum of invariants. So what is clear for now is that these axioms determine, they determine at most unique possible such C, because all the birational maps will be decomposed into blow-ups and blow-downs with smooth connected centers. And then the result actually is the existence. So some comments here that, so okay, C stands for centers. This invariant is kind of writing down all the centers with a plus or a minus, depending whether it's a blow-up or blow-down. And also the statement that needs generalizations to higher dimension once we decide what is the codomain of the map. Here is just kind of points with the Galois action. Higher dimension, there will be some kind of birational types of certain dimensions.
Don't you need characteristic 0 in higher dimension for weak factorization?
So in characteristic 0, I would define it differently. I would look at exceptional divisors, and then I don't need weak factorization, interestingly enough.
Okay.
Yeah, there's a version in any characteristic. Okay, so what about the proof? So kind of after you believe the statement, the proof is not difficult, but it's a little bit surprising that this thing is defined. So let's just think a little bit how one would prove this. So one way to make a proof simpler is to think about exceptional divisors as opposed to centers, because exceptional divisors, so centers require a choice because we need to choose a factorization, and exceptional divisors are just canonical. And then as soon as one phrases this invariant in terms of exceptional divisors, which are P1 bundles over 0 dimensional schemes, nicely this P1 can be always canceled because the exceptional divisors This is how it is. And then we can reconstruct the centers from exceptional divisors and then see that everything makes sense. Yeah, so it's slightly surprising, but not a difficult result. Any questions or comments here? Okay, so we move on. I'll speak about some examples. So we can take two surfaces, or we can just take one surface and look at its birational automorphism and the invariant X values in the Burnside ring. And basically, we'll be proving that for a single surface, this map is zero map. So like, how should be this a zero map? So for example, if K is algebraically closed, I said it's not a very interesting case. What happens is that a birational automorphism will blow up the same number of rational points as it will blow down the P1s. Therefore, obviously, this is zero by the Néron-Severi group considerations. A bit more interestingly, if you take any element of finite order, and usually birational maps of surfaces have a lot of this, then its invariant is zero just because we take values in a free abelian group. And more generally, so-called regularizable elements, namely the ones conjugate to regular automorphisms, they also tend to zero formally because the target is abelian. Therefore, everything which is conjugate to, kernel is a normal subgroup. Everything conjugate to a regular map will go to zero. So this looks a bit boring, but in fact, we'll see more interesting geometry coming from Sarkisov link and how this C works in interesting cases. Okay, so now I said I'll formulate the main results in a couple of ways. So the first formulation, which is the most flexible one, is that if you take any two surfaces and then consider the value of a map, birational map between them, the C of phi, then the result is independent on the choice of the map. So it may look a bit funny like this, but a corollary is that if we take x equals y, we get a zero map, just because we have identity, and constant in this case will mean everything goes to zero. And this first theorem is just a way to, so in this flexible formulation, it's easier to prove when we allow the whole groupoid of birational types as opposed to look at each surface individually. Okay, so we'll be proving the result a bit later in this, as in the theorem, independence on the choice of the map. So explicitly, okay, you may think, why is it interesting something is zero? So I define something which is a zero map, but in fact, it means something constructive. It means that what I said at first, that for any choice of factorization of phi into blowups and blowdowns, the centers of blowups will match the centers of blowdowns up to isomorphism. So that's something which holds for 3 folds over C and doesn't hold for 4 folds over C. So why else it's interesting? Because, okay, the C in general is not a zero thing. So in the other part of this work, which deals with higher dimensional varieties, this is the way to construct maps from Cremona groups to integers, which is something which wasn't known before. So it works for, depending on the station, it works for some fields and not other fields. Okay, so now what I'll do, I'll explain relation to the Grothendieck ring, and then I explain some parts of the proof specifically for rational surfaces. Okay, so we change gears a little bit. I'll speak about some general structures now. So I guess many people would have seen this before. So for any field, we can define something called the Grothendieck ring of varieties. It has generators, isomorphism classes of varieties. We can take quasi-projective or all varieties or schemes of finite type here because of the relations. Relations are cut and paste. For every closed Z, we have one relation like this. And finally, to make it a ring, we take K product of varieties. And a fine line often plays an important role, and it's called the Lefschetz class L. Okay, so I give 3 open questions about this ring. So firstly is, if X and Y are smooth projective with the same class, are X and Y birational? Some comments about this. So in characteristic 0, the famous Larsen-Lund's theorem says that those are stably birational, which is slightly weaker. And furthermore, if X and Y are non-projective, then this is not true. So Grothendieck ring of varieties is very easy to define, but it's counterintuitive in some way, because equality of classes may mean that we have to add some higher dimensional bits, do some rematching, and then geometric meaning is lost. So specifically, just equality of classes of non-projective varieties doesn't imply that they are birational. Secondly, question of L equivalence. So it's known now that L is a zero divisor. Again, it's the same work of Borisov. And the question I propose here is to find out geometric meaning of L equivalence and also full description of the annihilator of powers of L. So examples exist for certain types of varieties, namely elliptic curves, K3s and Calabi-Yaus, but no general picture is known. In particular, it's not known how close this L equivalence is to derived equivalence, even though all the examples we have are derived equivalent. And the third question, which has sort of less of geometric content, but still is some curiosity, is K0 torsion-free, or is it a free abelian group? Or does it contain torsion? So kind of, it's completely unclear. Any comments or remarks here? So I've got a message, I think. Yes, someone asked what is annihilator of L infinity. So I look at annihilator of each power of L, and informally this is the union of all those annihilators. It's just something annihilated by some power of L. Yeah, thanks for this question. Okay, so we move on. I explain now the relation of this talk to Grothendieck ring. For this, we introduce truncated version of the Grothendieck ring, namely, we allow varieties up to dimension D. So generators are like this, relations are like this for all varieties which are allowed, so up to dimension D. And then, so it's not a ring, obviously, but there is something like a partially defined product. Sometimes, if dimensions are not large enough, those can be multiplied. So, okay, example 0, if we restrict to zero-dimensional varieties, we get exactly the Burnside ring, because relations will simply be disjoint unions of zero-dimensional schemes. A bit less trivially, if we restrict up to 1, because every curve has a unique smooth projective model, we can split this Grothendieck group as direct sum of zero-dimensional stuff plus smooth projective one-dimensional stuff. But you see, we're using here uniqueness of models. Okay, so in general, we have this whole inductive system, and the K0 of varieties is a colimit of this system. So every generator and every relation comes from some finite level in this tower. And I comment in a second why these are non-injective. That's some of the things which makes the Grothendieck ring quite difficult to understand. Okay, so here's the reformulation of the main results I'm speaking about today. So it's simply this exact sequence. So I have my K0 of varieties up to level 2, and the last map is taking two-dimensional bits to their birational types. So BIR2 is the set of birational types of surfaces. And the claim is that the kernel of this is exactly K0 of varieties up to 1, which is, as I said, just zero-dimensional plus smooth projective curves. So you may think it's not a big deal, but this result is kind of equivalent to what I'm talking about. So in particular, okay, what do we see? That K0 of varieties up to dimension 2 is a torsion-free, so actually even a free abelian group. Equality means birationality. If you have two classes of curves or two classes of surfaces which are equal, then those guys are birational, just because that's how the sequence work out. And L equivalence is trivial. There's no way we can multiply by A1, which is something like, there's no L equivalence of curves in this setting. Right, so it looks a little bit trivial, but in reality, it's not. So kind of, if we want to study K0 of varieties, where we know that, so for example, we know that curves can be L equivalent, that L times the product of two curves can be 0 in this big ring. Whereas on the level 2, we're showing it's impossible. So in particular, these maps are not injective in general. So we add non-trivial relations at every level. Are there any comments or questions here? Okay, so we move on. Okay, so I'll speak a little bit more about my invariant C of phi and L equivalence. So the basic relation is that as soon as we have a birational map between X and Y to surfaces, then their classes in the Grothendieck ring differ by L times those centers, C of phi. So what do I mean here? So we can see, so C of phi was defined in the Burnside ring, but we can map it into the K0 of varieties and consider it there, and there multiply by L. And this statement is very easy. By the weak factorization, we just have to look at a single blow-up, where the statement is simply the blow-up formula in the ring. So I spoke before about the choice of sign for this C, and the sign is chosen so that the target surface is the source surface plus the centers we write down. Okay, so what, yeah?
Are you saying it works for surfaces or in arbitrary dimension?
So in this talk, I only defined C for surfaces. So yeah, on this page, X and Y are surfaces. That's right, thanks. For surfaces, it's especially straightforward, this kind of formula. Okay, so what is the relation to L equivalence? So let's start with a false proof of the main result. So the false proof from the result is this. I just divide by L and claim that it's independent of phi because on the right-hand side, I don't have phi. But in reality, the question is, where does this belong? Because it's not a combination that I want anymore. It lies in some localized ring and the geometric meaning is lost. So the specific problem is that we don't know whether L can annihilate differences of zero-dimensional schemes. So if we knew that such schemes would have to be isomorphic, then it would be done, and this would be the correct proof. But in reality, we don't, and I think it's impossible to get this from general principle. To get something like this, one have to do lots of birational geometry. So what do we know about L equivalence of fields? We know very little. So we know that if, using cohomological tricks, Italic cohomology and Gassman triples, one can find out that if you have a Galois extension, it's okay, or if the field is of small degree, it's okay. But if you have two fields of degree 6, already we don't know the status of this question. Okay, so maybe I'll try to summarize the relationships I was talking about in a diagram. So this is the diagram. There are links, 3 links between 3 concepts. So what about 1? So 1 is not what I am talking about today. That's just some general wisdom about Grothendieck ring controlling rationality problems. So the first bit is Larsen-Lund's theorem. Then there was my work with Galkin on cubics. And then there was specialization by myself and Nik S and Kantsevich-Schinkel. And it's all about Grothendieck ring as a device to control rationality. The second is what I was talking about before. So how, if we know L equivalence, we know C of phi, and conversely, controlling C of phi gives us information about the truncated Grothendieck ring. And finally, there's a third part, which I'll be speaking about soon, that how rationality, there's idea of rationality centers. If you have a variety which is rational, you may want to know why it is rational. This means which centers does a birational map blow up and blow down. And so knowing the image of C on the set of birational maps between your fixed rational variety and projective space tells you about all possible ways of relating those two by blow-ups and blow-downs. So specifically, it seems doable for surfaces, and that's something we're currently thinking about. So I'll now do some proofs, namely in the rational surface case, and this will also include those rationality centers I was talking about for Pezzo surfaces and conic bundles. So maybe we step back a little bit and discuss what the surface of a perfect field is. So it's quite a fun story, going back to Enriquez, Mann, and Teskovskih. And actually lots of the proofs I'm talking about today will have to do with the work of Teskovskih. So the claim is that minimal surfaces over perfect fields are of the following types. So firstly, non-geometrically rational case where extension to K bar is not a rational surface. Then we have, so this is the most general case, surfaces with an F canonical class or conic bundles over curves of positive genus. Then we have a geometrically rational case. So XK bar is rational. We can have a conic bundle over a conic or a minimal del Pezzo surface of Picard rank 1. So these 3 and 4 are the work of Manin and Dyskovskih. So to prove our main result, we need to look at each connected component of the groupoid of birational types. Namely, so we can look at those types 1, 2, so we can look at those types separately. So 1 is the biggest amount of surfaces, but the result is trivial because all birational maps are biregular. This is more or less equivalent to uniqueness of the minimal model in those cases. Second is not difficult because birational maps are easy. Namely, birational maps will be over this curve because it's positive genus. So all -1 curves will be in the fibers. And then one proves that, one classifies birational maps between those guys. And 3 and 4 is the main case. So this is like the smallest amount of surfaces, but there is the largest variety of birational maps between them. And this is what I'll be talking about soon. Okay, so what I'll be explaining is the proof for the main result, namely this constancy of the invariant for minimal rational surfaces, so which is a subset of 3 and 4. If we understand this case very well enough, everything else is simpler than that. Okay, so how do we treat these minimal rational surfaces? So I said that they are either del Pezzos or conic bundles in the geometrically rational case, but for rational case, we can be much more specific. Namely, here are the types that minimal rational surfaces can be over a perfect field or actually over any field. We have P2. We have twisted Hirzebruch surfaces, so conic bundles over a conic. And in fact, over algebraic closed fields, this is all we can get as everyone knows, P2 and Hirzebruch surfaces. Now, over non-closed fields, we have some other option. We have del Pezzos. So it could be something like a quadric, minimal del Pezzo of degree 8, del Pezzo of degree 6, and del Pezzo of degree 5. So in each case, the Picard rank is 1 or 2. And a note for experts who are disappointed to see no more conic bundles, namely the ones which have degenerate fibers, they are not listed because they are del Pezzos. That's one of Dyskovskih's lemma, that like all the conic bundles in those degrees, which are rational, will be del Pezzos. So they're already listed. So that's not quite like a minimum model where I care whether my thing is fibered or Fano. It's more, I group them in a slightly different way. And I call these surfaces in the list models of large degree. So basically, these are surfaces I'll be working with. So you can imagine there are also models of small degree, namely the ones whose canonical squared is 4 or less. And those are, minimal ones are not rational, and there are much fewer birational maps between them, and they are much easier to deal with than these guys. Any questions or comments now?
I don't quite see how do these surfaces like cubic surfaces, minimal cubic surfaces match into the list on your previous page.
Why do you say minimal cubic surfaces?
No, I mean, say del Pezzo surface of small degree, minimal del Pezzo surface of small degree, in which part of your list from the previous page.
Minimal del Pezzo of degree of rank 1, for example, the number 4.
Okay, so you're saying that you will explain only K rational surfaces. You will not explain K bar rational surfaces.
The older terminology is to say rational for geometrically rational. And for me, rational is rational over the ground field.
So you're only talking about rational over the ground field.
Yeah, this list can, you see, for example, why there's no cubic surface here. That's because the theorem of Laskovsky says that minimal cubics, or maybe Manin Laskovsky, or maybe just Manin, minimal cubics are not rational. Yeah, okay. So there's certain game between large degree and small degree. So in terms of what is easier, what is more difficult, so like the surfaces in this list are geometrically easier just because they are rational as soon as they have a point, for example. And cubics are complicated, but from where I'm coming, cubics are easier because cubics have just a few birational maps. They have such a low degree that all those links I'll be talking about only connect them to degree 1 or 2, and there's easy to deal with. Okay, yeah, maybe we'll see some of this soon. Yeah, so there's this concept of rationality center I want to introduce. We're getting a little bit technical here. I already said that interesting Galois sets may come from lines on del Pezzos, but in fact, I'll be caring not about lines, but about conics and twisted cubics. So conics come in pencils by Riemann Roch, and twisted cubics come in nets, also by Riemann Roch. And I look at this for del Pezzo surface as G sets, and it's a nice exercise in each degree to compute how many of these there are, similarly to the known numbers of lines on each of those. Okay, so here is this technical definition. So I want to assign a certain Galois set to each module of large degree from the last slide. And I call it NSX because it will have to do with Neron-Severi of my surface. Okay, so here we go. So for P2, I assign a fixed point. There's no action. For a conic bundle, I assign 2 fixed points. Again, there's no action. Now it's getting more interesting. For a quadric, I assign the set of its ruling. So conic bundle structures on a quadrics are the same as rulings, and there are 2 of this, and this is my Neron-Severi set. Then for del Pezzo of degree 6, I think, Sasha, you may recognize this case. We have, we look both at conics and cubics, and then we take away fixed point. That's really a virtual set as opposed to effective set. And then a fun exercise is to see that there are 3 conic bundle structures and 2 nets of twisted cubic on such a thing. Okay, the final case we have to cover is del Pezzos of degree 5. There are 5. So it's all about 5 on del Pezzo degree 5. There are 5 conic bundle structures. There are 5 nets of twisted cubics, and they are isomorphic. It's a similar thing to why on a cubic surface, lines and conics are the same thing. It's similar. So 2 plus 3 equals 5. It's a nice exercise. Right. So these are my sets, which I assign to each of the models of large degree. So you kind of ask, why do I want to do this? But in fact, to prove what I'm going to prove, that something is independent of the choices, I'll have to give some explicit answer for this constant, and it will be in terms of these sets. So, okay, why the notation NSX? So in each of those cases, the Neron-Severi group over K bar is a Galois module with rational coefficients will be a permutation module. That's just a property of those surfaces being rational. And I choose a representative for the corresponding Galois set, or virtual Galois set, like in the case of del Pezzo of degree 6. So this explains the notation, but the language, yeah, okay, maybe. So I'll try to illustrate everything on a quadric. So for a quadric, Neron-Severi is generated by 2 rulings, and that's exactly what I chose to be my set, the 2 rulings. And the other cases work very similarly. Okay, so we use notation Neron-Severi, but we call it rationality center for X. So why do we do this? So I'll explain this partly on the next slide, but what do I mean by rationality center? So if X instead was not a surface over a perfect field, but a complex cubic fourfold, rationality center is something which we're supposed to blow up when we connect our X to projective space. And specifically for a cubic, it's expected to be a K3 surface. So we want to keep track of this kind of data, and we call it rationality center. And the next slide explains why those are rationality centers. And I'll comment on the quadric case again on the next slide. So any questions or comments here? Okay, I move on. Okay, so here is what we'll be proving in reality for rational surfaces. So previously I was claiming that, okay, so C of phi is independent on the choice of birational isomorphism. Now we are specific, C of phi is a difference of these two rationality centers attached to one surface and the other surface. So what are remarks in particular, we get what we claimed before, but a bit more precise form. And okay, so maybe a little bit on rationality centers again. So let's take one of the surfaces to be P2. Then if you remember from the previous slide, its rationality center is a point, so 1 in some sense. And so the result then is saying that if I have a rational surface and connect it to P2 by blow-ups and blow-downs, I always get the same thing, namely I get this rationality set attached to the surface, okay, -1 maybe. Yeah, so we control not only a single construction of rationality, but all constructions of rationality for a given surface. So this is something where it goes much more complicated in higher dimension, that different K3 surfaces can be both associated to the same cubic fourfold. Okay, so here is the example which hopefully will make sense. So I look at a quadric with a rational point. Why is that rational? It's rational because we blow up the point. We obtain 2 - 1 curves, which are disjoint and we're coming from the ruling of the quadric. We blow those down and we get a P2. This is kind of one way of looking at this diagram. The other way is you start with a P2, you blow up a Galois orbit of 2 points and contract the line through them. That's the inverse to this map. In any case, what's important is that if you ask your quadric, who is your rationality center? The quadric should say, my rationality center is this Galois set of my 2 rulings, because that's something which is created by map from P2 to Q, and yeah, or blown up the other way. So kind of from the perspective of the quadric, it's rational because like its rationality has to do with its sets of 2 rulings. And this is an example for the theorem because C of phi is what it should be. It's like we add 1 and remove this pair of Galois points. That's quite fun example to play with, and lots of things are seen in it. So, okay, so this naturally leads us to Sarkisov links. Sarkisov links is a certain generating set for birational isomorphisms. And that's something which is known in no dimension, but in dimension 2, it's something very explicit. So the result, going back to Iskovskih, is that for surfaces, all birational maps will be decomposed into links of 4 types. So I don't define all of those types. I'll speak about type 2, which is the most interesting type. So what is a type 2 link between Del Pezzo surface? So that's a diagram of the following kind. I have 3 Del Pezzos and maps, and maps are birational and regular, and Picard rank of surfaces downstairs is 1, and upstairs it's 2. So basically we blow up Galois orbits on both of these maps. And in fact, in this talk, we already have seen 2 examples of such links. So Iskovskih lists 26 of this. I counted it earlier this week. Some of them come with inverses, so it's a bit less in practice. Okay, so what are the 2 examples I already told you? Standard Cremona transformation, you blow up a Galois orbit of 3 points, contract 3 lines. This is 9, 6, 9, which are degrees of Del Pezzo involved. By degree, I mean k². And the one from the previous slide, which was rationality construction for a quadric. 8 is k² for a quadric, then I blow up a point and contract 2 lines. And Iskovskih lists 26 things which look a bit like this. Okay, so what are we going to do with those links? The point is that everything is set up in such a way that allows to checking link by link. So let's see what I mean. So originally, for rational surfaces, we plan to show that C of phi is independent of the choice of the birational map between them. And note that here I'm I'll be needing this flexibility. So if I was only speaking of self maps, I wouldn't be able to apply any links because the links are generators for groupoid, not for individual birational automorphism groups. As I announced first for rational surfaces, the result takes the form that C of phi is the difference of the two rationality centers of those surfaces. So because of the additivity of C under compositions and the flexible way of stating the result, we just have to check each Sarkisov link. So we need to verify a certain finite number of things. And what's important here is that Sarkisov links only relate models of large degree to other models of large degree. So if you look at delpetzos of degree 5 and higher in Iskovsky's list, they're only connected to delpetzos of degree 5 and higher. Okay, so there are 4 types of links. Type 4 is an isomorphism changing the two conic bundles on the surface, and types 3 and 1 are mutually inverse. So we just check one of those. And so we don't have to check all the links. There are some tricks, namely Etal homology, Gassman equivalence, and L equivalence of fields, which which allow to prove the statement for some types of links without doing any computation. Namely, I explained that if we knew results about L equivalence for all fields, we would easily get the main result. But if we get partial results for L equivalence, we can still plug them in and just rule out or check easily many types of links. Some of the links which are involved are involutions, and it's quite nice because for finite order elements have C equals 0, and this is how it should be. Okay, so actually out of all of those links, we just have to deal with 636, 646, 835, and 945, which are the degrees of the delpetzos involved. So you can see that, okay, so if you kind of know what links are, you can see that the only links which I have are, which have 3 or 4 in the middle. So why is that? Maybe I can explain some of the tricks. So if I have a 1 or 2 in the middle, then the link is Geyser involution or Orbitini involution. And I don't have to check those because those go to zero. And if I have conversely higher degree in the middle, maybe 5 or 6 or 7, then I'll deal with L equivalence kind of thing. So just there will be no room for anything to go wrong for high degrees. So these are degrees in the middle which have to be checked individually. And I explained one of these, which, yeah, and all of them are similar. Okay, so what is our link of the day? It's delpetzos of degree 6. And namely, I proved the link 6, 4, 6. So let's see what this link does. So it's all about minimal delpetzos of degree 6, which are not necessarily isomorphic. So my link is not an involution, and the surfaces are not isomorphic. So recall what the rationality centers of those surfaces were. So I had to take A plus B minus a point, which I now write as 1. So A's are pencils of conics on my delpetzos. I have 3 of those on each of them. Yeah, so this slide is a little bit technical. So we are getting to the end of the talk, and now I'm speaking to experts in delpetzos who may enjoy this kind of thing. And B's are nets of twisted cubics, which there are 2 on each of my surfaces. Now, what does link do? The link does the following. So we blow up a Galois orbit of 2 points and contract something. So what do we contract? We contract minus curves, which we acquire after this blow up. What are those minus curves? They are exactly the proper preimages of twisted cubics passing through my center. So twisted cubics have square 1. When they pass through 2 points I blow up, they square to minus 1. So these are exactly my 2 minus curves, which are blown down in the second part of the link. Now, by symmetry, the first part of the link will actually blow up the Galois set corresponding to the twisted cubics on the second delpezzo. And this way I get B of one surface minus B of the other surface. So that's just what we get by inspection of what gets blown down, what gets blown up with Galois actions. All right, so yeah, so then one can can check in this case that the corresponding sets of conics are isomorphic for the two del Pezzos, we definitely see that del Pezzos themselves are not isomorphic because this B and B prime can be different Galois sets. And then, therefore, if we take one minus the other, we get the desired result. And so there are some links like this to verify. Okay, so I'll be finishing up. So right, so what's the summary? The summary is that our main result is that for birational automorphisms of surfaces, centers of blow-ups and blow-downs correspond to each other up to isomorphism. So as I explained when I was speaking about connection to the Grothendieck ring, this would be trivial if we knew that L equivalence of fields, or more generally, étale algebras, is trivial. So we don't know such a result. And furthermore, I think we cannot get it formally. So much work goes into controlling the truncated Grothendieck ring that I don't think there's any magic device which would rule out L equivalence of fields just by general reasons. Yeah, so, right, so our result gives us control over the truncated Grothendieck ring, and if we want to study Grothendieck ring in more detail in higher levels, we just have to do more of birational geometry, things like Sarkisov links and MMP. Okay, so for rational surfaces, which is the case I was concentrating in the proof, the main result is equivalent to the fact that no matter how we relate P2 to our rational surface, we always get the same thing, and we call that thing its rationality center. And those are defined in terms of conics and twisted cubics on the Pezzo surfaces. And finally, as I made clear, the proofs are applications of the minimal ball program and Sarkisov links, which are fully classified by Skovskih. Okay, so this is what I want to say. Right, so this is the end of the talk. So I know that it's maybe difficult to ask questions in Zoom, but if you have any questions or comments, please feel free to send me an email and I'll reply to you. Yeah, thank you.
Thank you. Thank you very much for the nice talk. Questions? So I have a question. So what was the definition in the case of complex projective varieties of higher dimensions? You have mentioned that you have one of the Ori variant.
Yes. So okay. So maybe I'll go to that definition I stated. Right. So in higher dimension, the way to go is to think about exceptional divisors. So kind of on the right side, we'll get ruled ruled varieties of dimension n-1. And then they will be the map is defined by taking exceptional divisors of our map minus exceptional divisors of the inverse map. So it will be all about exceptional divisors. And then it will satisfy the same three conditions where we interpret the second one creatively, namely sort of up to stably birational equivalence or birational equivalence.
Okay.
Wait, it's a follow-up question. What is the target of your map in higher dimension once again?
Yeah, so you see, there's some choice involved. So the easiest thing I can do is stable birational types. We can be more specific and look at birational types of n-dimensional varieties which are ruled. So kind of, there's some choice involved, but I guess the best we can currently do is birational types of n-1 dimensional ruled divisors.
And when you say birational types, you mean the free abelian group on stable birational types?
Yes, that's right. But nicely for surfaces, P1 times a field determines this field by its global sections of the structure sheaf. Therefore, multiplying by P1 of the center for surfaces doesn't change anything. Therefore, the image nicely lies where the centers should lie. Whereas for higher dimensional thing, we cannot divide by P1 anymore, and we should think of this rule divisor as an invariant. The story has a bit different flavor in higher dimension, namely, yeah. So it's not as clean as this story here.
Other questions?
Maybe it's a little bit of a side question, but do you believe in L equivalence for fields or not?
Yeah, that's an excellent question. So I don't know. You see, so our guiding principle is that L equivalence should be related to D equivalence, right? And we know that D equivalence for fields is trivial, right? Because if we have derived equivalence of two zero-dimensional smooth schemes, we can recover the scheme. So probably it shouldn't hold non-trivially, but all the current motivic avatars of this notion, I can have zero-dimensional schemes with isomorphic Chow motives. And therefore, there's no way I can use some realizations to solve this. So I don't know.
Oh, okay, thank you.
Other questions? If not, let's thank Evgeny again, and so we'll proceed at 3:30 New York time.
Okay, thanks, Ludmila.
Thank you.